All right, good morning, everyone. Let's get started. So this is the last week of lectures. This is going to be my last lecture for the semester. And then on Thursday, Professor O'Donnell will give his last lecture. So I titled this lecture, Life After 251, because I think, after this course, there's going to be a big void in your life. I mean, what are you going to do with your weekends? Right, so I want to tell you in this lecture what you might want to do in your weekends from now on. But first, let me maybe try to capture how you feel right now with 3 movies. Okay? So the first one is Shawshank Redemption. Second one is Braveheart. And then the third one is Django Unchained. Well, you're not the only one who thinks that way. So as instructors, we also have similar feelings. But no, like all jokes aside, actually, we did have a lot of fun teaching this course, and we hope that you enjoyed it as well. Now, what I want to do first is maybe do a little recap of what we covered and what we learned. So this is like from lecture 1. What were some of our goals? Our first goal was to learn about theoretical foundations of computation. Another goal was to learn the basic math topics, the language that we needed to study the theoretical foundations of computation. Become better at reasoning abstractly and formally. Become better problem solvers. And the 5th one was not in the original list, but I added it for this time. So become better at expressing yourself clearly. And I think over the semester, based on my interactions with you guys in office hours, I'm happy with the growth that you have shown in these respects. So what are the topics that we learned? So some core topics that we learned. We started with formalization of mathematical proof. We then looked at formalization of computation. We looked at deterministic finite automatons, DFAs. We looked at Turing machines. We studied computability and uncomputability. We studied computational complexity. With respect to mostly time, but also with respect to space complexity. We looked at circuit complexity here as well. And along the way, while we were doing this, we tried to present you some interesting algorithms to present to you some the power of algorithms and how they can actually do some surprising things. So then the next big topic, important topic, was MP completeness and the P versus MP question, the famous P versus MP question. One way to deal with MP complete problems is approximation algorithms. We looked at that. And then another main topic that we covered was randomization. And randomization appears in many places in theoretical computer science. For example, in cryptography, it's pretty essential that we have randomness. Maybe with respect to polynomial time computation, we don't expect randomness to help too much. That's what we think. But in the case of communication complexity, for example, we proved that actually randomization does give us more power than deterministic protocols. Right, so the equality function had a very efficient randomized protocol, but the best deterministic protocol was the worst possible in terms of cost. And then after these core topics that we discussed, we looked at some selected topics, not maybe necessarily in the core, but still very interesting and important topics in theoretical computer science, like cryptography, Markov chains, quantum computation, communication complexity, and the computer science perspective on proofs. And along the way, of course, we also covered the mathematical tools that we needed. So, for example, we talked about a little bit of set theory, in particular infinite sets, the concepts of countability and uncountability. We spent like 3 lectures on graph theory. It's extremely important in computer science. We spent 2 lectures on probability theory, again, very important. We did like a bit of number theory, modular arithmetic. We did fields and polynomials, and we did 1 lecture on linear algebra. So, we hope that now you can appreciate how these different areas of mathematics come into the picture, come into the study of computation. And of course, there are other tools that we didn't discuss. There are other very interesting topics that we didn't discuss, but we try to do some of the important stuff. Now, what I want to do is actually give you present to you some interesting and big open problems in theoretical computer science. Some of these problems are already problems that we have seen, and I will also add some questions that we did not see already. This will be a completely biased list of problems, okay? It's problems that I find interesting, most interesting. There are many other problems that are interesting to study, but I have limited time, so of course I'm going to talk about stuff that I like. And maybe this gives you an idea about how to spend your weekends moving forward. Okay, so the first area I want to talk about is the relative power of resources in computation. So what are the resources, some of the resources that we looked at? Time, obviously, space, randomness, and non-determinism. Non-determinism captured by let's say, the complexity class NP, non-deterministic polynomial time. So problems whose solutions can be efficiently verified. We could add to this list, I guess, quantum resources, but I have a separate section on quantum, so we'll discuss that later. The most famous open problem that we know, and it's appropriate to start with that, is does non-determinism help with respect to time-efficient computation? Or in other words, the famous P is P equal to NP question. We can also ask, very similar type of question with respect to space-efficient computation. This is captured by the L versus NL question. So L is the class of languages that can be computed in logarithmic space. NL is the class of problems whose solutions can be verified in logarithmic space. And this is not as famous as the P versus NP question, but still an extremely important question. Morally, you can say it's as important in some sense. Another very important question, actually I like this question even more than the P versus NP question, is time equivalent to space with respect to efficient computation? Or let's capture this question with the following one, is P polynomial time computable functions problems equal to the class of problems that can be computed in polynomial space? Okay, so time equivalent to space with respect to computation. Time and space are important concepts in physics as well, and how they relate to one another is an important problem in physics. And we have an analogous question in computer science as well, and I think it's a very interesting question. Now note that we know that P is a subset of NP, and NP is a subset of P space. So this question is actually, it's probably easier than the P versus NP question. It's definitely not harder than the P versus NP question. And potentially, it's much easier to solve than the P versus NP question. Okay? Because if you separate P from NP, obviously you separate P from P space as well. Okay? But, this seems to be, some sense feels like an easier problem to tackle. And it's actually, think about it, quite surprising why we haven't been able to tackle it. In the sense that, it seems like obviously they're not equal. It seems like obviously in polynomial space, you can reuse the space over and over and over again and do exponential time computation. But, you cannot reuse time. Right? You cannot reuse time in the complexity class P. If this was maybe a physics course, we might declare P not equal to P space as a postulate, as a fact of life, and move on. But that's not how we do things in math. So we want actually a proof. An actual proof of this. And then another very important question, does randomness give us more power with respect to time-efficient computation? So we can capture this question with the following one. Is P equal to BPP? So what is BPP? So that stands for bounded probabilistic polynomial time. And it's the class of problems which can be computed in polynomial time with a randomized algorithm, with a randomized Turing machine. Does every randomized algorithm, efficient randomized algorithm, have a efficient deterministic counterpart? Now we believe that, actually, we have reasons to believe that P is equal to BPP. So these two classes are actually equal. And that in the Turing machine world, randomness does not really buy you extra power. And there's also an interesting connection to circuit complexity, it turns out. So I'll give you a very high level description of this connection. So it turns out that if you prove some certain circuit complexity lower bounds, then that implies P equals to BPP. Certain circuit complexity lower bounds that we don't know how to prove, but that we think that's true. And also, interestingly, P equals BPP implies certain circuit complexity lower bounds. Although, these two lower bounds are not the same kind of lower bound, so it's not an equivalence exactly, but almost an equivalence in some sense. So that's very interesting. Like, why would such a connection exist? It seems very surprising, but it's actually true. So that's a nice connection. One important result in this area that we briefly mentioned is that primality testing is in polynomial time, can be done in deterministic polynomial time. Why is this important? Because, well, prime numbers are important, first of all, but secondly, the primality testing problem was like the canonical example of a problem that we knew how to do very efficiently using a randomized algorithm. We had no idea how to do it with a deterministic algorithm. algorithm. So it was a big result when we could show that it can be done by a deterministic polynomial time algorithm, which strengthens our belief that P equals to BPP. Now, with respect to randomness, another interesting question that you can ask is, does randomness give us more power with respect to space-efficient computation? And we can capture this question with the following question. Is L equal to BPL? BPL is bounded probabilistic log space. So the probabilistic analog of log space. And again, an interesting, important result here, analogous to the fact that primes is in P, is that undirected ST connectivity, the problem where you're given a graph, undirected graph, and you're given two vertices S and T, and you want to know if S and T are connected or not. Okay, this problem has a very natural randomized log space solution, but for a long time we had no idea how to do it with a deterministic log space machine. And this was shown in 2005, and it was a very big result, and again strengthens our belief that L equals to BPL. So you look at all these questions, P versus NP, L versus NL, P versus P space, P versus BPP. These are all major questions, and all questions that we really don't know how to tackle. Why? Because when you want to show that, let's say, P is different from MP, we want to find a problem in MP that cannot be solved by a polynomial time Turing machine. Okay, so or if you want to show L is different from NL, find a function, find a problem in NL that cannot be solved by a log space Turing machine. So you need to prove lower bounds. You need to prove that certain Turing machines cannot compute something. So if you come and say, oh, I've proved one of these things, I will ask for your lower bound. And this happens to be a major challenge for us. Like, we are really, really terrible at proving lower bounds. Okay, and this is one of the reasons why these problems are still open. Now let me move on to circuit complexity, because you can think of circuit complexity as an approach to proving lower bounds for Turing machines. Okay, so why do I say that? So if you recall, circuits are they have a very clean and simple definition for computation. They're just a composition of extremely simple gates, AND gate, OR gate, and NOT gates, right? And in contrast, like Turing machines, they don't have this kind of nice, simple definition. They're more messy to work with. If you remember from, I don't know, week 3 or something, more complicated definition. So it's really much nicer to work with circuits. And we know that there's a nice connection between the two. We know that if you have a problem that you can solve with polynomial time Turing machine, then there is actually a polynomial size circuit for that problem. And if you take the contrapositive, that means that if you can show that a certain problem does not have polynomial size circuits, it cannot be computed by polynomial size circuits, then there's no polynomial time Turing machine that can compute it. Right? So this is a valid and interesting approach to proving lower bounds for Turing machines. So you could say, why not just show that the SAT satisfiability problem, which is NP complete, we know, cannot be computed with polynomial size circuits. If we can do this, then we can separate P from MP, and we can collect our $1 million. But life is not that easy. But it's still interesting, this approach, because it gives us a starting point, definitely. So let's take a circuit with OR and NOT gates. So what researchers did in the 1980s, they were like, okay, so we're not, maybe it's a bit ambitious right now to just prove a lower bound for general circuits. Let's just restrict it, make this circuit less powerful so that we can try to prove lower bounds. And that's a common strategy in math. You're given a problem. If you don't see how to solve it, make it simpler, solve the simpler version, and hope that the techniques that you come up with to solve the simpler problem will lead you to hopefully to solve the general problem too, or give you insights about this general problem. So one very obvious restriction that you can apply here is let's restrict the depth of the circuit to be, let's say, constant. So let's say depth 100, I don't know. So it's not allowed to grow with the input size, with n. And one of the major results in computational complexity theory is that such circuits, when you just have constant depth, in sub-exponential size cannot compute the parity function. What's the parity function? You just take the sum of the input bits and you look at it mod 2. You take the parity of it. Okay, so that was a very interesting result, non-trivial result, an interesting result. And then the next step is, of course, all right, so we can beat these circuits when they have constant depth. Let's give it a bit more power and let's see if we can beat them when they're a bit more powerful. So you can ask, what about order, let's say, log n depth? And unfortunately, we're stuck there. So in particular, for example, parity can be computed in polynomial size when you allow log n depth. So that doesn't work. And we don't know really how to prove lower bounds here. But there's another direction actually you can go. Okay, so if that doesn't work, let's try to make the circuits a bit more powerful in another way. And what we're going to do is we're going to allow parity gates. Okay, so we showed that constant depth circuits in polynomial size, they cannot compute parity. We want to make progress. We want to make these circuits a bit stronger. Let's add parity as a gate. So now these circuits can compute the parity function easily. And now can we beat such circuits? Right? Now this is going to force us to come up with new techniques, new ideas, and hopefully we'll gain more insight about these things. Okay, and I say you add parity gates. And then we can show, again, these are all results from the 80s. Such circuits in sub-exponential size cannot compute mod 3. Okay. And mod 3 is like parity. You take the sum and you check if mod 3 if it's 0 or not. And a parity gate is corresponds to mod 2 gate, mod 2 function. And then since we're going in this direction, you can say let's add mod 3 gates to the circuit and see what we can do. So now you have and or not. You have mod 2 gates, and now you're also adding mod 3 gates. But you can say, instead of adding mod 2 and mod 3 gates, let's just add mod 6 gates. So that turns out to be equivalent. So we're going to have AND gates, OR gates, NOT gates, and mod 6 gates. Now, meanwhile, so we're trying to go in this direction. Now, let me cut that story in half. And let me tell you now another direction that people have been going. Meanwhile, in the 80s, another kind of restriction was that you removed NOT gates from the circuit. But otherwise, the depth, there's no restriction on the depth or anything. Okay? So the only thing that you changed from the general setting was that you removed the NOT gates. And it was an amazing result in 85 that Razborov proved that such polynomial size circuits cannot compute the clique problem, which is an NP-complete problem. Now, if you could just extend this result so that you also allow NOT gates, then P is different from MP. You've done it. And there was reason also, people had this intuition that, NOT gates, when you want to compute the clique function, should not help too much. So this result seemed to to come very close to showing P different from MP. So at this time, people were quite excited, and they were like, okay, we're going to solve this problem, no problem. But that's basically where we're stuck right now. So no progress. Well, there has been some progress, but pretty much no very important progress has been made since that time. So I can tell you the current frontier in circuit complexity is the following. So the other direction where we were adding mod 6 gates, that's also where we're stuck. So find a language in NP that cannot be computed by constant depth polysize circuits with AND or NOT and mod 6 gates. Okay. So we don't know how to do this. But in fact, I will show you something even more surprising. In fact, this is not even known. Find a language in NP that cannot be computed by depth 3, okay, only depth 3, polysize circuits with just mod 6 gates. I don't allow you AND or NOT gates. You just have mod 6 gates, and you just have depth 3. Okay. So I'm trying to identify for you the simplest kind of circuits that we don't have a lower bound for. And I think there's even a simpler kind of circuit that we don't have a lower bound for. And so in fact, let me just change the definition, generalize the definition of a mod 6 gate just slightly. Okay, so let me call these a generalized mod 6 gate. And it's extremely similar to a mod 6 gate. It's just that you're given some subset A of 0, 1, 2, 5. Okay, and your mod 6 gate will be parameterized by this A. So again, you're going to take the sum of your input bits. Again, you're going to take mod 6 of that. And now, to determine whether you should output a 1 or 0, you're going to check if it's in the set A or not. A is called accepting set. Okay, so it tells you for which mod 6 values you should output a 1, you should accept. Okay, I mean it's very similar to regular mod 6 gate. You're still doing mod 6 counting. Okay, you're still adding these up and doing mod 6 counting. It's just like when do you output 1 and 0 depends on what A is. And now here is the from my perspective, the simplest kind of circuit for which we don't have a lower bound for. So find a language in NP that cannot be computed by depth 2 polysize circuits with just generalized mod 6 gates. I mean, it doesn't get simpler than that, right? So depth 2, you cannot have depth 1. Depth 1 is just one gate. Depth 2 is you have one output gate that and then you have other mod 6 gates that feeds into this one output gate. And that's what it is. It's extremely simple, it seems like. Mod 6 gate is an extremely simple, stupid kind of gate. Like, I mean, it just counts mod 6. But we don't know how to do this. So please solve this problem, because it's really driving me crazy. Okay. Now let me tell you about an interesting connection between now circuit complexity and communication complexity. Okay, so we discussed that communication complexity has like lots of different applications. One of the applications areas is like circuit complexity, and there's an actually very interesting connection between the two. To present this connection, I'm gonna tell you about a communication complexity setting that is slightly different than what we learned in class. In particular, it's going to be different in the sense that there will be not just 2 players, but there will be more, like there can be an arbitrary number of players, let's say k players. And the model that I'm going to describe to you is the number on the forehead model, NOF, short for number on the forehead. And let me now describe you the model with just 3 players, but it will generalizes to an arbitrary number of players easily. So let's say we have 3 players. So Ryan, Tom, and Tim. So again, like they each get an n-bit string. So Ryan gets x1, an n-bit string. Tom gets x2, an n-bit string. Tim gets an n-bit string x3. But now the situation is a bit different, because why do we call it number on the forehead? So player I sees all strings except xi. So the way you visualize the scenario is that, you know, Ryan has his input written on his forehead. Okay, so x1 is on his forehead. So he doesn't see x1. Okay, and similarly, you know, Tom has his written on his forehead, and the other players as well. So, you know, Ryan sees everyone else's input, everyone else's forehead, but the only missing information is like the input written on his forehead. Okay, so that's the model. You know, it seems like maybe a strange model, but it's actually a very interesting, useful model to study. It has lots of interesting applications. And you know, of course, again, just like the 2-player setting, you know, there's some function that they want to compute. So if it's 3 players, maybe it's just some function f that takes these n-bit strings as input, gives you a 0, 1 output. And they're going to carry out, you know, they're going to communicate with each other to compute this function. And when they communicate, you know, they have a common blackboard. You know, they write their messages on the common blackboard, so that, you know, I don't know, when Ryan sends a message, writes a message on the board, you know, all the other players see that message. Okay? So there's no like private channel between any 2 parties. Like whatever is communicated is seen by everyone. And, you know, similar to 2-player setting, we can define the deterministic k-party communication complexity of f for k players. And then we can define like the randomized k-party communication complexity of f, and so on. Now, what is the connection to circuit complexity? So let me tell you that. So we said the current frontier in circuit complexity is like, you know, find a language that cannot be computed by constant depth polysize circuits with, you know, and or not mod 6 gates. It turns out, if you want to do this, it suffices to do the following: to find a function that cannot be efficiently computed in this number on the forehead model that I described, when the number of players is polylog n. Polylog is like log n to the some power, some constant power. Okay? So you want to find any function, find me any function that does not have an efficient communication protocol, when the number of players is polylogarithmic in the input size. Unfortunately, we have what we call a log n barrier. So we don't have any lower bounds when the number of players reaches log n. So in some sense, the way you should think about this is that as the number of players increase, the model gets stronger and stronger. It can compute, in some sense, more and more functions. And when if we have like number of players is like goes up to log n, we have good lower bounds, strong lower bounds. But once the number of players basically reaches log n, we don't know. And this is holy grail of communication complexity, in my opinion. One of the most important problems in all of communication complexity. Okay, so then, coming back to circuit complexity, we can say, okay, what's the best lower bound we know if we don't apply any restrictions? And we actually seen this. So with circuits with and or not gates and no restriction on the depth, the best lower bound we know is 5n minus peanuts, which is quite, in some sense, sad and pathetic and frustrating. But that's where we are. Okay, so that's circuit complexity. Yeah, so actually before I move on, let me tell you in one slide another kind of interesting circuit. These are circuits with threshold gates. What's a threshold gate? A threshold gate can be defined as follows. So you're given some weights, W0, W1 up to Wn. And what you do is you take a weighted sum of the input bits. And then you see if this weighted sum exceeds some threshold. Let's call it W0. If it does, you output 1. If it doesn't, you output 0. Now, with a threshold gate, you can, for example, encode. If you pick the weights appropriately, you can encode an AND gate, you can encode an OR gate, and you can encode other gates. Why are we interested in circuits with threshold gates? There are various reasons for it. One reason you can say is that they sort of model, in some sense, a neuron in your brain. So it seems like a neuron works something like this, like a threshold gate. So in some sense, you can say like a circuit with threshold gates is an extremely simplified model of your brain. It's extremely simplified and not very accurate, but you got to start somewhere, so it's still interesting. So another major open problem in circuit complexity is find a function that cannot be computed by polynomial size. Again, just depth 2 circuits composed of only threshold gates. Okay. So why are circuit lower bounds so hard to prove? So these two guys, in '94, Steven Rudik, who's a CMU professor, and Rasborough, gave some answer to this. I think they were thinking like, okay, if we cannot prove lower bounds, then there must be a good reason why we cannot prove it. And they were able to show that in a very precise, in a formal way, that current techniques are unlikely to work. Okay, and this is now known as the natural proofs barrier for circuit complexity. So what they're saying basically is that you need to come up with new techniques to show or prove lower bounds for circuits. Okay, let's move on to algorithms. let me list some interesting upper bound questions, algorithmic questions. So one example we've seen is like the matrix multiplication one. I showed you a list of results, progressions on the exponent here. I actually forgot to tell you some recent developments in this area. So in 2011, the best exponent was 2.373, and then that was improved to 372 in 2014 by Francois Legal. And actually, maybe more interestingly, in 2014, they were able to show that these techniques are not going to let you go below 2.3. Okay, so again here, if you want to improve this exponent, you will need other ideas, new ideas. So of course, the mega open problem here is, can we go all the way down to n squared? And n squared is the best you can hope for, because the output matrix has n squared entries, so you need to be able to write those values down. So that will take n squared time at least. Graph isomorphism is another very important problem. Given two n-vertex graphs, are they isomorphic or not? We've seen this last lecture. It's a very interesting problem for the following reason. It's one of those few problems that is not known to be in P nor NP complete. So it's in NP, the graph isomorphism. It's easy to prove that two graphs that are isomorphic, but it's not known to be NP complete. Actually, there's evidence that it's not going to be NP complete. And if you ask people what they think about this, I think some people would say that they think it's in P, that can be done in polynomial time. And some people would say that it's somewhere between P and NP complete. So it's neither in P nor NP complete. So can you can either try to show that it's in P, or you can say, let's assume that P is different from NP. Now, can you show that, it's neither in P nor NP complete? Best known algorithm is of the form 2 to the big O of root and log n. So any improvement on this would be a very important result. The factoring problem is something we've seen already. Given a composite number, output a non-trivial factor. It's again one of those problems that not known to be in P nor NP complete. Again, there's good reason to suspect that it's not NP complete, but is it a P or not? We don't know. Best known algorithm is roughly 2 to the big O of n to the 1/3. Again, any improvement on this would be a very big result. And we know that there's a polynomial time quantum algorithm for factoring. Okay, so it's interesting with respect to that as well. Another interesting problem is finding an n-bit prime. So given n, output a prime number with at least n digits. Now what's interesting about this problem is that we want to find the polynomial in n time deterministic algorithm for this. But we know how to do it with a randomized algorithm, poly-n time randomized algorithm. We discussed this. So you can think of this as again, one of those few problems now that we know how to do efficiently using a randomized algorithm, but we don't know how to do efficiently with a deterministic algorithm. So in some sense, you can think of it as replacing the primality testing problem, which was such a problem. Now we have this problem, finding an n-bit prime. So this is a very big open problem. Now let's discuss quantum computation. Right, so this is like the future, basically, of computation. You basically, arrive at this concept by asking a very simple question to yourself. So we've seen that, computation is about information processing, right? So you can ask, what if we do information processing using the laws of quantum physics rather than the Newtonian laws of physics? And one of the first people who asked that question, what if we do information processing using quantum mechanics, is Richard Feynman. He's an extremely famous physicist. If you don't know him, I do recommend reading about him and learning about him. He's a very interesting person. So he said, for example, the only difference between a probabilistic classical world and the equations of quantum world is that somehow or other it appears as if the probabilities would have to go negative, right? So what makes quantum computation is interesting, what makes it different from randomized computation is that somehow the probabilities have to be negative, and then they can cancel each other out. And a positive probability and a negative probability cancels each other out, becomes zero, and then that event never happened. Okay, so that results in some interesting, spooky stuff. Now, there are some very obvious questions with respect to quantum computation. We can define, for example, BQP, which is the quantum analog of BPP. So quantum computation is inherently probabilistic. So we can compare BQP to BPP and ask whether they are the same or not. Does quantum computation give us more power or not? Now the answer to this, I guess most people would say that they think BQP is more powerful. For example, we can do factoring in BQP, but we don't know how to do it in BPP. And there are other problems, like the discrete log problem is also another example. Well, then you can ask, well, how powerful is BQP? Can it solve the traveling salesman problem? Can it solve the satisfiability problem? Can it solve an NP-complete problem in polynomial time using a quantum computer? So we can ask, for example, is BQP equal to NP? And here, actually, we believe, experts believe that this is, they're incomparable sets. And in particular, that we don't expect quantum computers to be able to solve actually NP-complete problems efficiently. The problems that seem like you can solve efficiently using a quantum computer, they have strong structure in them, like the factoring problem, like the discrete log problem. And that kind of structure is not there, let's say, in let's say, satisfiability problem. Now let me give you an open problem that is not obvious, but it is a problem that I find personally very interesting. So there's a very simple game called the parity game in which you can very easily see or prove the power of quantum mechanics. The game goes like this. So we have Alice and Bob, the usual suspects. But now we actually have a third player, a referee in some sense, Charlie. Now what happens is very simple. So Charlie picks two random bits, x and y, which they are each 0 or 1, chosen uniformly at random, and they are, x is given to Alice, y is given to Bob. Now Alice and Bob have to reply with 1 bit each. So Alice replies with a bit A, Bob replies with a bit B, okay, just 1 bit each. And they win, Alice and Bob, they're going to win if this condition is satisfied, that the XOR of A and B is equal to the AND of X and Y. Okay? That's the game. It might seem like a strange game, but it's actually a very important game in quantum computation. Because it really tells you, proves to you how quantum computation, quantum mechanics can give you more power over classical mechanics, I guess. So you can show it's like you can win, like Alice and Bob in the classical world can win this game with probability 75%. Why is that? Yeah. Yeah, so they can just output 0, and then since x and y are picked at random, the only way this is going to be a 1 is if they're both 1. That happens with probability 25%. The rest of the case, 75% of the time, this is going to give you a 0. Okay? So by just simply outputting 0, giving 0, they succeed with probability 75%. And you can show that this is actually the best possible. You can prove that the best strategy, they're going to win with probability 0.75. Now you can also ask what happens with quantum if you have a quantum strategy, and if, like, in particular, if they're allowed to share quantum entanglement. Not getting into details of this, but let's just say that with best quantum strategy, you can show that they win with probability 0.85 around, better than classical strategy. Now a big open problem is, why is 0.85 and not, let's say, larger? Okay, so we'll describe this situation in quotes like quantum entanglement enables two separated parties to exhibit classically impossible correlations. But why is the correlation capped at 85% and not higher? Because it could be, the correlation could be all the way up to 1 probability 1, and it wouldn't really violate anything. Okay, so from a physics point of view, there's no really good explanation why this number is not larger and it's like 85%. So that's an important question that you can ask. Why is it 85%? Okay. And there's an interesting angle you can take here using communication complexity, actually. So a result from 2005 is that if we could achieve success probability 1, we show that then the deterministic communication complexity of any function is at most 2. Communication complexity becomes trivial. So you can say, like, if we take as a fact of life that communication complexity is not trivial, then here's an explanation why quantum correlations cannot be like, let's say, 1 per 100%. And another result, same year, along the same lines, improves this basically in some sense. If you could achieve success probability, let's say like 90.8% or more, then the randomized communication complexity becomes trivial. Every problem has like 2 bits solution. So you can say, you know, if we take this as a fact of life, as an axiom in some sense that, you know, in our universe, communication complexity is not trivial, then you can say that gives you an explanation of why the correlation cannot be more than 90.8%. Okay, but there's still a gap, right? So what happens when the probability is between 85 and 90%, let's say? Okay, so I think this is a very interesting problem. Okay, so I told you some like interesting open problems. Some are probably harder than others. So how are we going to tackle these tough questions? Okay, so is it going to be a solo effort? Okay, a solo type thing. For example, Andrew Wiles in '95 proved Fermat's last theorem. That was an open problem for 358 years. And you know, he worked on it alone in secrecy for like 6-7 years. And then he solved it. He did it. So a very impressive solo effort by Andrew Wiles. Is this the way, you know, big theorems are going to be proved? We can ask maybe, you know, are we going to prove it in a group setting? So here, for example, a very great mathematician, Paul Erdős, who lived from 1913 to 1996, he had like more than 500 collaborators in his life. And there's actually a number, Erdős number, which is the degree of separation from Erdős. So Erdős himself has Erdős number 0. If you have co-authored a paper with Erdős, you get Erdős number 1. If you have co-authored a paper with someone who co-authored a paper with Erdős, you get Erdős number 2, and so on, right? And most people I know, like in the area, I think have Erdős number at most 4 or 5. I don't remember meeting someone who had a larger Erdős number. So that, you know, kind of shows you how much he collaborated with people. He was an interesting guy. He referred to children as little epsilons. Yeah. Mine is 3. Okay, so then we can say, okay, maybe this is the way, you know, we're going to make progress in math problems, or maybe we're going to go open collaboration. So there's some interesting directions here as well. There's, for example, what's called polymath projects, massively collaborative online mathematical projects. So, you know, we have the internet now, you know, we can communicate with each other quite easily. Can we like gather all the mathematicians in the world, and can we like just sit down and think about a problem all together and make meaningful progress? So one of the famous mathematicians, Timothy Gowers, Fields medalist, he has a blog, Gowers web blog. I mean, I recommend that you follow it. So he asked this question: is massively collaborative mathematics possible? And you know, he actually started a project like this, and you know, different mathematicians from all around the world came together, and they actually turned out to be extremely successful, and they were able to solve an important problem. Actually, Ryan was one of the contributors as well in this, and I'm sure if you asked him, he would be happy to tell you more about it. But this is an interesting direction. Okay, so should we solve problems in this way? Or is this more efficient way of solving things? Open collaboration. Maybe we could come up with a new category. Let's maybe call it comp, where you use the assistance of computers maybe to come up with proofs. So like a four-color theorem can be a nice example of that. So you reduce the problem to checking 2,000 cases, and then you let the machine check for the 2,000 cases. But you can imagine, like in the future, there will be more meaningful interaction between a computer and a human being as AI progresses. Maybe the machine can give you new ideas. Maybe you can help the machine prove things, and that's an interesting direction. And if the AI people are really successful, you could have like Solo for comp kind of problem where, given some math, the machine will be like, this is easy stuff, and will not even need our help to do it. Okay. Well, whatever the case might be, whether we do these things together or we need a stronger AI or whatever, we will need your help to make progress on these questions. And I'll end, I guess, the lecture with a slide from lecture 1 and a quote from David Hilbert from 1900. Okay, thank you.